It's important to do some problems with STP because they can be a source of confusion. STP is just specifying temperature, which is 273 Kelvin, and pressure, which is 1 atmosphere. So nothing more, nothing else. All right. So the temperature of 2.5 liters of a gas, that's the volume, is raised to 200 at STP. Okay, so at STP, is raised to 250 degrees C at constant volume. Calculate the final pressure of the gas in atmosphere. All right, so STP should automatically tell you that we're talking about 1 atmosphere and 273 Kelvin, and we have this volume here. So we have a new temperature. Let's call this T2, and let's really quickly convert it to Kelvin. So that is 423 Kelvin, okay, adding 273 to 250. At constant volume, calculate the final pressure of the gas. Okay, so we have a volume V1, but the volume is constant, so the volume is going to stay the same at 2.5 liters. The temperature has changed from 273 Kelvin, 423 Kelvin, so it's been raised. The volume stays the same. We want to find the new pressure. So it seems to me that this is a Charles law problem sort of wrapped with that STP label to try to confuse everyone. The constant volume means it's just going to stay at 2.5 liters, so no worries there. So Charles law, if you remember, is P1 over T1. We have some pressure P1 at some temperature T1. We change 1 and we get a new pressure, or we get a new temperature. Okay, we have a pressure at 1 atmosphere. This is all what STP entails. We've changed things. What they did was they've increased the temperature to 250 degrees, so from 273 K to 423 K. Actually, this is 523 K. Okay, just caught my mistake. 250 plus 273 is 523, so I cannot do basic math, it seems. 273 plus 250 is 523 Kelvin. All right, so our T2 here is 523 Kelvin. And I'm glad I caught that error before I went ahead and finished the problem. And calculate the final pressure. Okay, that's going to be P2. All right, so P1 at T1 at STP conditions, we have a new P2 once we raise the temperature up to 523 Kelvin. All right, so we have 1 atmosphere at 273 K, and we need to find the new pressure at 523 K. Okay, that's going to be my new P2. Always cancel out your units. Kelvin cancels, leaving us with atmospheres. So 1 times 523 over 273, getting 1.92 atmospheres, 1.92 atmospheres. So let's put this to 2 significant digits. So we'll call it 1.9 atmospheres. All right, so that is an STP problem, STP conditions, but utilizing Charles law. Let's do another STP problem here, okay, because even though it's just a temperature that's 273 and a pressure that's 1 atmosphere, a lot of people get confused. All right, so this is an interesting problem here. Calculate the volume in liters of 88.4 grams of CO2 at STP. Okay, so the answer here, people would love to jump in and say, oh, you know, they'll hop on the bandwagon and say 22.4 liters, and that is not something you want to do. That is not the right answer. It would be the right answer if we had 1 mole of this gas CO2. We don't know how many moles we have. Let's go ahead and convert it, and then we can figure out if we do have 22.4 liters. Gas CO2, let's go ahead and convert it to moles. For every 1 mole of CO2, there is about I believe the answer is 48. So 88.4 divided by 44.01, about 2.00 moles of CO2, or 2.01 moles of CO2, really doesn't matter, 2.00, 2.01. So that's not 1 mole. Okay, so that's definitely not 1 mole. It's actually not 1 mole, it's 2 moles, so we would expect it to be double 22.4. But let's go ahead and solve for this using the ideal gas law. R is something I'll give you, so don't worry about it. 0.0821 liters times atmosphere over mole Kelvin. Okay, our temperature at STP, remember, is going to be 273 Kelvin. And our pressure at STP, remember, is going to be 1 atmosphere. All right, let's do our cancellation of our units here. And yep, I'm getting 44 on my calculator, 44.8 liters as my answer. Okay, so STP problem, don't just jump and think of 22.4 liters. Okay, you have to make sure you have 1 mole. If you don't have 1 mole, then you got to go through this step using the STP conditions of temperature and pressure.